Okay, just a kind of a quiz here. I want you to work this out. Well, leaves the ramp, velocity 3 meters per second, angle 20 degrees below horizontal. Find the x and the y component vectors of the velocity. Okay. So you have v vector plus u. Okay. Here. So I'm just writing kind of small here. So the v vxi plus vyj equals vector vx plus vector vy. You might not be able to read that, but underline that notation. Then, if the ball falls 1.2 meters, starting with this y velocity, then it doesn't matter if it's going off the edge of the ramp, starting with that y velocity, or just somebody tossed it downward with that y velocity. Falls 1.2 meters, starting with that y velocity. How long does it take? And you will use your equations of motion to answer that question. You use vectors to answer the first question. Okay. So everybody got that, at least framed the problem correctly to where I'm confident you'd get a right solution. Even if you didn't get through all the calculations. So here we have it. For the first question, you really want to draw a picture of this velocity. And it's 3 meters per second. That's 20 degrees below the x-axis. So you're going to immediately get v, and I said vy, that's the one we really want, is negative v times the sine of 20 degrees. It's negative because obviously, now when you draw this, you want to reinforce what it means. And I'm not sure I saw everybody do that. So I just really encouraging you to do it. So here's Vy, and here's Vx. Okay. Vy, which I write without the arrow, as I pick up the chalk that just slipped from my grasp. And I've got two short pieces. Okay, well, I've got that. Okay. Vy is going to be in the negative y direction. So I could actually write Vy equals Vyj, and Vx equals Vx pi. Good idea to do that. Remind yourself of the difference between an arrow over the component and without the arrow. Okay, and to reinforce the I and J components, which I think everybody's pretty good with. But okay, so Vy is this, which equals negative 3 meters per second sine of 20 degrees. And the sine of 20 degrees is kind of around a third. So that's about negative 1 meter per second. I think people get like 1.3 something like that. Okay. The 20 degrees is about a third of a radian. It's still a small angle. So as you hopefully learned in calculus, the sine of a small angle or the tangent of a small angle is approximately equal to the angle. But you better not be thinking it's equal to the angle degrees, because then you get like sine of the angle is 20. So it can't be bigger than 1. Okay. So sine of 20 degrees, which is about the sine of a third of a radian, For a small angle, it's about a third of a radian, so that's where I get the 1, and that's even at 20 degrees, that's a good approximation. Get up to 30 degrees, it's not quite. Okay. You should understand, there's a picture you get in a calculus class when you start proving the derivative of sine and cosine. And I'll be reminding you of that picture at some point. Well, actually, here's the picture, see if it's right. This distance is sine theta of the circular definition. This arc length is theta, because this is the unit circle. And the arc length is just the angle times the radius. Okay, and we see that theta and sine theta are very close. The arc distance here for a small angle is very close just to the vertical distance, even closer than it looks in this picture. Kind of exaggerated the difference. If you get up here, an angle like this, well, the arc distance is a lot longer. So the approximation no longer holds. That's something you should really understand. You might want to go back to the calculus book. Look up, why is it that sine theta is close to theta? You probably see this picture, it's a standard picture. So hopefully you saw it and this reminds you. That's going to come in handy many times in course. Well, that's a digression, but that's how I got to -1 meter per second without having to resort to that complicated calculus. Why push buttons? What do you do in your head? Depends how accurate you want to be. I'm just trying to illustrate it. You're engineers or medical practitioners, as the case may be. You want to be exact, or as exact as you can. So that's okay. Still, it's important to be able to do quick and dirty calculations. Well, the cosine of 20 degrees is, I'd say it's about 2.8 meters. Question on that, I'm pretty sure I'm within the 10th. Okay. I wouldn't be surprised if I actually got it. Okay, so that's easy. So Vy. V equals Vx plus Vy equals approximately 2.8 meters per second I minus 1 meter per second times J. And again, everybody either got that or knew which equations they were going to use and would be able to get it. Okay. Okay, so let's say we're pretty quick about this because you know engineers are in statics. You get pretty used to doing calculations with your trigonometric functions. Next thing we want is to have to answer this question in free fall. Now V0y is -1 meter per second. AY is within 2%. It's 2% less than -10 meters per second. And even my lab allows you to use 10 meters per second squared. Okay, I think I said 10 meters per second. Okay. So it allows you to make that approximation. I've talked about that before. And for most applications, unless we're trying to be really precise, that's good enough. Now for lab analysis, probably want to use 9.8 because we might be able to obtain enough precision to be within 2%. So there's your AY. And your I'll say y equals, and I like yeah, I'm just gonna use y equals 1.28. Yeah. We'll find t. Well, find an equation that has these variables along with t, and that would be um, I'm gonna modify what I'm doing here. I've written this as a y minus y naught over here. I think your book has the equation has a y naught over here with a plus. But since we usually know the displacement, which is y minus y naught, don't really need it over here in many cases. If you want it over here, put it over there. It's the same equation, whether you have a negative y naught here or y naught here. Okay. So now solve for t. And what we have is a quadratic equation. Now there are easier ways to do it because there are other quantities we can use with these to find like VF squared. You know, your squared velocity is equal to your squared initial velocity plus 2 times acceleration times your y minus y naught. Okay, might be easier to do that. I'm going to show you how that's equivalent just because it's good to know. Okay, we solve for t. There you go. We get the quadratic equation. So we put it into this form. Now, sometimes I want to put the numbers in here with the units and everything. Sometimes I don't. Okay. Here, it's pretty cluttered if you try to just put all the quantities with units into the discriminant and stuff, the p squared minus 40 and all that stuff. So I'm going to choose not to do that. And really, that's what you're both to. And in this case, it's a good idea because the intermediate quantities you get aren't that considered. Okay, so writing out the equation again. We have this of t equals, well, I assume everybody knows the quadratic formula. If not, get it into your head. Look it up, it's straightforward. You just, here's your A, here's your B, here's your C. And this and A, not to be confused with accelerations, coefficient squared. B is coefficient of t, and C this. Okay, well, plug all that in. Get negative V naught y plus or minus the square root of V naught y squared minus 4 times 1/2 a y times negative y minus y naught, all divided by 2 times 1/2 a y. Just straightforward plug in to the quadratic formula. Okay, just a little sloppy with my y minus y naught here. That needed to be in parentheses with a negative sign in front of it because you have to do the negative. C quantity. Put down the negative here, negative here. You get what you get. We have this. Okay. Well, now we're stuck having to put our numbers in. Okay. I don't like to suppress the units, but I'll just say, make sure the units work. Okay. The units of velocity over acceleration are typically meters per second divided by meters per second squared, which is meters per second times second squared per meter. Meters divide out, 1 of the seconds divides out, and you get seconds, which is better because you're looking for time. So that works. Okay. Now, square root of V naught y squared. Well, square root of V naught y squared is going to have units of V naught y, which we've already seen are seconds. Okay, units of time. And you can think, time, length over time divided by length over time squared, stuff like that. Whichever way you want to think about it. It's a little more intuitive, just to think of meters and seconds, SI units. But it's more general. But do it the way the book explains. Okay, anyhow. Then an acceleration times a displacement. It's like meters per second squared times meters, which is meters squared per second squared. And the square root of meters squared per second squared is meters per second. So this, well, this and this both have units of meters squared per second squared. So when you take the square root, you get meters per second. Again, over meters per second squared gives you seconds. You want to do all that. Give you a test. You don't want to see all that. Either that or put the units in here and deal with the sloppiness. Okay. It works either way. And I often put the units, but I'm not going to this. So V naught y is negative of -1. That's 1 meter per second. But plus or minus. Now it's convenient. I didn't set it up that way. I just did a little initial velocity. And it happened to work out, but this is just 1. And then AY is 10 meters per second squared, y minus y naught 3.2 meters. And AY. So you get 1/10 plus or minus. Well, the square root of this, that's 24, that's 25. Oh boy, that comes out nice. I didn't set it up that way, just like that. Okay. But that's a square root of 25. And if I did my arithmetic right, that comes out plus or minus 5/10. Doesn't necessarily agree with what everybody got. And that equals 4 seconds or negative 0.6 seconds. All right. I'm not sure. Okay. Okay. It was just pointed out to me that my chalk keep jumping over. That's what it was. At least that's my excuse. Okay. So yeah, you get 6/10 or negative 4/10. Obviously, 1/10 plus 5/10 is plus 6/10. Okay, so that's even worse. Well, I thought about it for a minute and said, oh, wait a minute. AY is negative 10 meters per second squared, right? Okay, so means I have a negative there. That's part I can do, right? For simple algebra, but it doesn't look like it, does it? So what's if I put okay, I set the problem up, I was careless. I was looking for the number. I got so busy looking for the number, I forgot to use my brain. But look at these numbers. What's wrong with this? If you assume upward is positive, and you don't have to, you could set your y-axis downward if you would, and all these quantities to be positive. But your y minus y naught is negative 1.2. So I was careless here, and then I wasn't thinking, and that's always a mistake. Unless I overthinking, and maybe it's not. Okay, so that's kind of a bonehead thing. But that ought to be negative 10 here, negative 1.2 here, but more importantly, you get a negative 10 down here, which then makes this negative 1/10 plus or minus negative 5/10. That doesn't matter. Plus or minus negative 5/10, it's the same thing as plus or minus 5/10. So that equals what? It equals what I said it equals when I was wrong, but now I'm right. Okay. So don't do like I did. Work it out a little more carefully. Think it through a little better. So it's 0.4 seconds. If we compare this to what we get if we start from velocity 0, we're going to get a little bigger number. It's probably going to be around 0.4445 seconds. I'm not seeing that with the number. Okay, anyhow, one way to check this. Okay, just a couple things about the equation. One way to check this is to say, okay, that means the average velocity was 1.2 meters per second divided by 0.4 seconds. Okay, negative 1.2. The average velocity is negative 3 meters per second. Okay, so one way to check is to say just intuitively your average velocity now, well, your sorry, v y, your final velocity, would then be By plus AYT, that's -5. Okay. And that's going to be greater 1 meter per second. It's 4 meters per second. So that does equal. That's got to be minus 4 meters per second because they want negative. Okay. Let's take it. Del. Okay, so there's our final velocity. And average velocity. -3 meters per second. And of course, the average Y velocity. Is -3 meters per second calculated just from your displacement divided by the time. So everything's an agreement. One more agreement. You don't have to always check all these things out. But getting used to the equations and thinking about what they mean and what they're telling you, it's a good idea. To do all the detail you can on a few problems. Okay. We also have you know, Y squared is -1 meters per second squared. 2A is 10 meters squared, 2 meters per second squared, multiplied by your 1.2 meters, right? It's 2 times 10, so that's this, including the meters and stuff, just so we see how that works out. So that's 1 meter per second squared and 24 meters per second squared. Meters squared per second squared. So dy is plus or minus the square root of 25 meters squared per second squared, which is plus or minus 5 meters per second. Okay, now we get a plus or minus. Which one applies to the situation? Well, the one that applies to the situation is the one where the thing is going down. Depending on how you got your axis oriented, it'll either be positive if your axis is oriented down or negative if your axis is oriented up. We discard the extraneous solution we get from the quadratic formula. Just like we discarded this extraneous solution, which would correspond to the negative, to the plus 5 meters per second squared. What that means is, if this thing was thrown upward at 5 meters per second, it would reach its peak, okay, 0.4 seconds later. Actually, 0.5 seconds later, reach its peak. And if t is 0 at the peak, then t was -0.6 of a second when you threw it upward. So you could have thrown the ball. The ball could have been projected upward, spring or something on the floor, projected upward at 5 meters per second. It's going to go up 1.2 meters. Then it's going to start its fall. But it's got to go up more than 1.2 meters. Sorry, go up more than 1.2 meters, start falling. When it reaches the 1 meter per second, which would be at the 1.2 meter height above the floor, comes back down. Okay. Now, it really didn't do that because it really moved on a ramp before. It wasn't sprung up from the floor, but it doesn't make any difference. Okay. So I used to go to conferences before they banned me. Claimed that reality was full of phantom projectiles. Okay. And I got a little wild-eyed about it. I got other jackets and stuff and tried to calm it down. Okay, well, not really. I'll explain phantom projectiles when we get to projectiles. But basically, what I just described is a phantom projectile up to this point and down to here. And then reality takes over. Now it's falling. Okay. And that phantom projectile is part of the parabola. In this case, it's a really skinny parabola because it's a straight up and down line. Okay. That's been going on since the beginning of time, and this ball just picked it up when it needed it. So you have infinitely many phantom projectiles going around, and when a projectile goes through there, it just picks one up and goes forward. What could this look like? Everybody decided not me, but no, it's worthwhile. I have a funny image of that in some wildlife before doing that. There's a point to it. There are things in physics that are just that weird. Much weirder than that. Okay. And when I started doing it, those things didn't even exist, multiverse and stuff like that. It might have existed if it does exist, but it did then. And nobody had thought at that point. Okay, all that aside, this gets us into projectiles. So if this thing is also moving at what we found earlier, this thing's also moving at 2.8 meters per second in the horizontal direction, then how far does it go in the horizontal direction? What would you measure if you did this experiment? The one we did, you could go, where we measure those distances on ramps. Okay. So work it out. How far would it go? In the horizontal direction, if this was its initial velocity, and if it had 1.2 meters of fall. And you get the answer very quickly if you understand what you see in the homework or what you actually see in the lab. You got your numbers. One you need is a 2.8 meters per second. Get this built back up very much in a minute, but I'll let you work on it. Okay, you've seen the demonstrations and the problem set. Okay. You've seen that the speed in this direction doesn't change. Okay. Now, for this situation, Vx is unchanging in free fall. This is so for any ideal projectile. In the demos you've seen, in the experiments we've done, that's been the case. There's a little bit of air resistance, which does slow the thing a bit. But it's so negligible, we can't observe the effect of it. Now, if we were using a ping pong ball, And there's a problem rolling a ping pong ball down a ramp because it bounces. Unless you have a really smooth ground. Okay, there's a ping pong ball, and friction's also gets to be a problem. But if you get a ping pong ball, there's enough air resistance that a ping pong ball will slow to the extent that we could measure it if we measure carefully. Okay, it doesn't slow much. If I take a sacrifice piece of graph paper, there's still a ball laying around here. Okay. If I drop these together, which one's going to hit the floor first? How far ahead is it going to be when it hits? Show me with your fingers how far you think it'll be hit. This far, this far. I mean, it's, about 5 feet to the floor, more than 5. Okay. Now this surprised me when I did it. Prepare to be surprised. That much difference. Okay, but that's measurable. Okay. And that much difference comes down to a time that would be measured in tens of milliseconds. Not a lot of time, hundreds of a second. Okay. So I hope you carefully watch the demos. They don't take long, and they give you a picture that you just can't get out of your mind, even if you want to. Then you just got to apply that picture. Okay, they're excellent demos. Saves me the trouble of trying to set things up, and they have better equipment anyhow. Okay, so demos and experience show that GX is unchanging each of the fall. Also, the physics, and of course, the physics explains the demos. Okay, so empirically, by observation, we see that in situations similar to the one that we used in lab, Vx is unchanged. Okay, physics is the only point in the X direction is air resistance. Okay. It has negligible effect on an ideal projection. So unless you're trying to shoot a golf ball 500 yards, you pretty well ignore air resistance. I played a lot of golf. Fairly low handicap, so I had to worry about a lot about air resistance. Okay. Didn't worry about it enough sometimes, but I should have. Okay. So what do we know? We're constant velocity, no force, no acceleration. Now pretty soon we'll start analyzing forces and see that the net force and acceleration are closely connected. And by Newton's second law, which some of you might have heard of. Okay, acceleration is 0. So. Okay. I'll run out the units because it's kind of a good idea. Really thinking you use everything you can. You know, X is what, 2.8 meters per second, or whatever more accurate value you got when you solved it. Just minus, that's our acceleration. Well, that's a good calculation. Doesn't really get us where we want to go. We will find X minus it's not far. So, I wrote this down. Here it is. And I don't necessarily regret doing it because it shows you the units again. And it shows us that the equations tell us that the velocity is unchanging if the acceleration is zero. That's worth being aware of. The obvious. If it isn't. Okay. Then your x displacement x minus x naught is v naught xt plus 1/2 axt squared, which is just 2.8 meters per second times 4 seconds, plus 1/2 of 0 meters per second squared times t squared, which equals then, this is approximate, but then if I multiply this out, I get 1.12. 1.12 meters plus 0 meters, which is 1.128. Okay. Does all that make sense? Because your next assignment is going to be building on these ideas. One of the big ones is ain't no acceleration in the x direction. Okay. Assuming you put your y-axis either up or down in your x-axis. Y-axis vertical, x-axis horizontal. No acceleration in the horizontal direction. No acceleration perpendicular to the gravitational force. So I'm to write that down. That's a big deal. Zero acceleration perpendicular to gravitational force. That's right. Okay. Now, we notice if we analyzed this same problem, assuming that the that the initial y velocity was 0, and that's exactly what we did, and that's what you did in your analysis of a projectile going off the end of the ramp. So, well, let's just assume that x component of the force is equal to whatever velocity you've got when you dropped it. Okay. When you divided your distance by 0.44 seconds or whatever it was. Well, let's work it out with that assumption and see how much difference that makes at 20 degrees. It's not going to make a lot of difference, but it is going to make a difference that we could measure. Then the question is it a difference that really makes, that's really detectable at the smaller angles that we use? Because our angles only went up to like, what was it, 1.6 degrees or something like that, or 2 degrees. I know one of the first angle was like 0.48 degrees, typically, half a degree. So if you use 4 dominoes, you get an angle change of about 2 degrees. Okay. And the sine of 2 degrees is what? Well, 2 degrees is about 2/60ths of a radian, because a radian's about 60 degrees. It's actually 57.1 degrees, okay, about 5% less than 60 degrees. The ballpark, it's about 1/30, okay? So if your speed down the ramp was 1 meter per second, and I don't know that you concluded speeds of 1 meter per second, but you got close, 80-some centimeters per second. You might have got 1 centimeter per second. Speed's 1 meter per second. That means that your vertical speed would have been 1/30th of a meter per second. 1/30th of a meter per second. Plug in for the V naught y in the quadratic equation. It's going to make a whole lot of difference. So it probably doesn't make much difference, but we want to analyze this week whether it's a measurable difference. And also we want to be able to analyze the projectile motion if we know how far the thing goes and don't assume that the initial velocity is 0. So we'll establish that at 20 degrees, there is a significant difference. Okay, that's really what we're after. And we'll put all that together. That's how we're doing it. We want to understand that thing we did in the lab almost 2 weeks. Okay, a week and a half. And that you've been writing up. And I'm going to give you more write-ups this week based on what we're doing here. Okay, so very similar to what we're doing here, but you really want to consider that. So we ignore Vy. That is, we assume that Vy is 0. V naught y. Okay. So if instead of the negative 1 meter per second, we have initial y velocity 0. We're going to get this. This is the same equation we had before. I went ahead and put the units in this time. But you can take that equation and just replace the negative 1 meter per second by 0. You check out the units, you can check out the units here. It comes out, comes out in seconds. The square root comes out in meters per second, divided by meters per second square, gives you seconds. Okay. And that's approximately equal to it's wrong, it's just come out longer than it should. Think about this for a second. Okay. And this comes out 0.49 seconds. Okay. I had you using 0.44 seconds. It actually should have been 0.49 seconds. Well, all your results could change accordingly. This is different than the 0.44 by about 11 or 12%. That would change some of your answers in your analysis. Okay. But I'm going to have you reanalyze. Well, I'll figure out what I'm going to do. Okay. That's closer to half a second. And then we get x minus x naught is 2.8 meters per second times 0.49 seconds. Well, multiplying that out, we get about 1 point less than 1.4, 1.37 meters roughly. Right. And that makes a significant difference because the time of fall that we got before was 0.4 seconds because we had that 1 meter per second downward velocity. Okay. If we ignore that downward velocity, we do get a very significant change in our prediction of how far it went. Okay. So that leads us to reanalyze. I'll probably have you reanalyze one case. All right. This time, here's the 0.49 seconds. That's just going to give you about a 10% increase. Actually, more like 9%. No, more like 11% increase in your predicted velocity. Okay. Now, everything you did in your analysis up to this point was tentative, just to get used to the equations and so forth. I gave you the 0.44 seconds. That would apply if it went off the edge of the table. A 1 meter fall, 120 centimeter fall technique. Shouldn't take that much longer. I'll have you check out the numbers, okay? And what we're getting at, in addition to just getting this basic understanding of projectile motion, is a pretty complicated analysis of the data we have. Okay. We know the slope of the incline, so we know the angle the ball fell. We know how far it fell, and we know how far it went. analysis of that is going to require two simultaneous equations. And it's one of the harder analysis that you get in projectile motion. Our goal this week is just to build that, and then maybe check out the results. Might go into something else and do that, okay? Because you got good results. And we check those results to see if they make a nice tight ball. And we get them done, everything checks out against everything else. I think it will, because I think you've got really good results. Okay. Let me give you the overall scheme then for projectile motion. Okay, so our general scheme for ideal projectile motion kind of looks like this. Often we can get by with just this equation for the x. Okay. Because the other equations for x are pretty much, we got x equals v naught x, right? Or x is x minus x naught over t. Displacement over time is the intuitive equations. Now, these equations become much simpler. The vx squared is just going to equal v naught x squared, because vx is v naught x throughout. So we don't even have an analog to that equation. This equation just becomes this. And this equation just becomes this. So it really becomes much. So I kind of put this one in parentheses because it's obvious that x is 0. This one might be useful. If somehow you can find t using these equations, and you just know the displacement over here. Okay. So the big thing is these x quantities are completely different from the y quantities. Okay. F quantity independent of y quantities except t, which is the same for both. So if you find t on one side, you get t on the other. Now I'm just going to give you a little prelude just so you know what to dread. And what do the equations look like if we're given the information that we have from the ramp? Okay. It's kind of complicated because, well, just okay, so the rank data on a given trial, what do we know? Well, about 3 minutes. It'll take long to write it down. See if we got any thoughts. Okay, just quickly. The RAF data on a given trial, we know the displacement of the projectile in the x direction, displacement in the y direction. Projectiles after the instant that leaves the end of the ramp. We know the acceleration in the y direction, it's the acceleration of gravity. And we know that, of course, that's acceleration is 0. Pretty much all we know. Now we got information of the ramp. We know how its initial velocity. We know how far it goes. I don't want to write that as x minus x naught, because confused with this. So we write a delta S, and we know theta. What else do we know? For the ramp and the initial velocity of the projectile. So that now, knowing theta, at least we know that V naught x is v cosine theta, v naught y is negative v sine theta. Well, again, with all that information, things get pretty complicated. So I'm not going to ask you to analyze that until the end of the week after you've been through the problem assignments on projectile motion, but I'm going to ask you to kind of frame that situation by doing a little bit of analysis based on what you did last week. Okay.